Inductive logic programming is a subfield of machine learning that combines elements of logic programming and machine learning to induce logic programs from examples. The roots of inductive logic programming can be traced back to the early years of artificial intelligence research. In the 1960s and 1970s, researchers began exploring the use of symbolic reasoning and logic-based representations for knowledge representation and automated reasoning. Logic programming languages, such as Prolog, emerged as powerful tools for representing knowledge and performing logical inference. During the same period, researchers were also investigating methods for automating the process of learning from examples. Machine learning techniques focused on pattern recognition, statistical modeling, and algorithms that could generalize from a set of training examples to make predictions on unseen data. The fusion of logic programming and machine learning led to the birth of inductive logic programming. The idea behind inductive logic programming is to use logic programs as a representation language for expressing background knowledge and hypotheses, and to apply machine learning techniques to automatically induce these logic programs from examples. The foundations of inductive logic programming were established in the late 1980s and early 1990s. One influential paper during this time was A Theory of Inductive Learning by Raymond J. Mooney and Jude W. Shavlik, 1989. This work provided a theoretical framework for inductive learning in the context of logic programming, highlighting the importance of defining a bias, a set of restrictions on the hypotheses that can be induced. Another key paper in the early days of inductive logic programming was Learning Horn Clauses from Data by Stephen Muggleton, 1992. This paper introduced the concept of learning first-order horn clauses, which are logical statements in the form of rules. Muggleton's work laid the foundation for inductive logic programming algorithms that focused on inducing logic programs in the form of horn clauses. In the mid-1990s, inductive logic programming gained more attention and started to attract researchers from both the logic programming and machine learning communities. Several influential papers were published during this time, advancing the theory and algorithms of inductive logic programming. For instance, Inductive Logic Programming, Past, Present and Future, by Stephen Muggleton and Luc de Rate, 1994. Provided an overview of inductive logic programming, discussing its techniques, applications, and future directions. The availability of inductive logic programming systems and datasets further facilitated the development and evaluation of ILP algorithms. Systems such as Progol, FOIL, and Aleph provided tools for inductive logic programming research, allowing researchers to experiment with different algorithms and datasets. Inductive logic programming research continued to evolve in the late 1990s and early 2000s. Researchers explored various extensions and refinements to inductive logic programming algorithms, addressing challenges such as scalability, handling noise in data, and incorporating background knowledge effectively. Different algorithmic approaches, including bottom-up, top-down, and hybrid methods, were developed to tackle different learning scenarios. One notable development in inductive logic programming during this period was the incorporation of probabilistic reasoning. Researchers began exploring the integration of statistical techniques, such as Bayesian methods and Markov logic networks, with inductive logic programming to handle uncertainty and learn probabilistic logic programs. The application domains of inductive logic programming also expanded during this time. Inductive logic programming found applications in various areas, including natural language processing, bioinformatics, software engineering, and robotics. In natural language processing, inductive logic programming was employed for tasks such as grammar induction, semantic parsing, and information extraction. In bioinformatics, inductive logic programming played a significant role in gene finding, protein structure prediction, and molecular modeling. In recent years, inductive logic programming has continued to advance, driven by developments in both logic programming and machine learning. Researchers have explored deep learning approaches within the context of inductive logic programming, combining the expressiveness of deep neural networks with the logic-based representations of inductive logic programming. Inductive logic programming has also benefited from advancements in probabilistic programming, enabling the integration of probabilistic reasoning with logic programming and learning. This has opened up new possibilities for addressing complex and uncertain domains. In conclusion, inductive logic programming has evolved as a subfield of machine learning that combines logic programming and machine learning techniques to induce logic programs from examples. From its origins in the late 1980s and early 1990s, inductive logic programming has developed a rich theoretical foundation, algorithmic techniques, and practical applications in various domains. It has become a powerful tool for knowledge discovery and automated reasoning, bridging the gap between symbolic reasoning and machine learning. Ongoing research continues to explore new avenues and further advance the capabilities of inductive logic programming, paving the way for future advancements in the field of artificial intelligence.